Okay, hi guys. In the previous lectures, we were looking at the ionization energy. So now we'll be looking at the applications of ionization energy. So let's get started with applications of ionization energy. So first application is metallic property. We have metallic property. So it is defined as a tendency to lose valence electron which is inversely proportional to the ionization energy of metal. So metal property is actually inversely proportional to ionization energy. More the ionization energy, less would be the metallic property, or in other words, the tendency to lose valence electrons. So metallic property across the period decreases due to increase in ionization energy. We already know that across period we have discussed it before also, that the atomic size decreases or the Z effective increases, or the control of positive charge over, rather the fraction of positive charge over valence electrons increases. Hence ionization energy would also increase because it would require more energy to extract the electron from the valence shell as we go across the period. So ionization energy increases, so metallic property across the period would decrease as we go from left to right, and metals are placed on the left side of the periodic table, and non-metals and metalloids are placed on the right side of the periodic table. Okay, so as ionization energy is increasing, that's the reason probably why we are placing metals on the left side of periodic table, and non-metals and metalloids are placed on the right side. Okay, next, on moving down the group, metallic property increases due to decrease in ionization energy. So as we go down the group, Z effective decreases as we are adding more shells, or in other words, the affinity of positive charge towards the valence shell electrons decreases. So as a result, we find that the atomic size also increases and the ionization energy would decrease. Why? Because we will need lesser and lesser amount of energy as we go down the period to extract the valence electrons from the atom. So ionization energy would decrease or metallic property would increase. Okay, second property which we are going to discuss in the application of ionization energy is reducing property. Reducing property of metals. So reducing property of metals is defined as the tendency to lose valence electrons in aqueous solution which can be correlated with ionization energy of the element. So we can write that the ionization energy is, other we can write that the reducing character is actually inversely proportional to the ionization energy of the metal. More the ionization energy, lesser would be the reducing character. Reducing character means the metal would be getting oxidized in the reaction, but it would be reducing other substances or other elements or atoms or compounds present in the redox reaction. Okay, so if we look at it like this, that if we have M, which is a reducing agent in aqueous phase, it gets oxidized and forms M plus aqueous with a release of electron. So this reaction is the oxidation reaction or the role of a reducing agent. So if we look at it more deeply, then we can say that, let's say, delta H sublimation is the energy which is required to convert it into isolate gaseous atom Mg, and which on providing it with ionization energy converts itself into M plus G, and this is when we add water into it. So this energy H sublimation would be required, and this delta H hydrolysis would be released. Okay, So we can directly write HYD. Delta H hydrolysis would be to form M plus Aqueous from M plus G. So delta HF for the reaction can be written as, for this complete from M aqueous to M plus aqueous, can be written as plus delta H sublimation from M aqueous to Mg, then delta H ionization energy, this one, to convert Mg into M plus G, minus delta H hydrolysis, which is released when M plus G is converted back to M plus aqueous. So this is a delta HF for formation of M plus aqueous from M aqueous. So we can, in other words, we can see that this is the required energy and this is the released energy. So we can write that if required energy is greater than released energy, then delta HF is positive. If required energy is greater than released energy, then delta HF is positive, and the other way around, delta HF would be negative if required energy is lesser than released energy. Okay, so as delta HF becomes more negative, reducing property of the metal increases, because we can see that delta HF of this reaction, which is conversion of M aqueous to M plus aqueous, the delta HF for this same reaction becomes negative, hence the reaction would go forward, go in the forward direction, or would be product favoring reaction. More amount of M plus aqueous would be getting formed. So this implies that the required energy should be lesser than the release energy. So required energy, let's suppose this is constant value, because anyways we have to convert this M aqueous into Mg, but the only difference which can make a big difference in making delta HF negative is smaller value of delta HIE. So this means smaller value of ionization energy. Okay, so lesser the value of ionization energy, more would be the reducing character. Hence we can write, for example, that order of reducing property among alkali metals, order of reducing property among alkali metals would be, Li would be less, most reducing, having the most reducing character, then Cs, then Rp, then K, then Na. And why is this the case? Generally Li should be the least, but we know that the ionization energy of cesium would be the least among all the alkali metals, hence ideally it should be placed here. But on the other hand, the experimental fact is Li is the having the highest reducing character. And why is this the case? Because if we look at the equation of delta HF, we also have a delta H hydration into the picture. So delta H hydration for Li is very high. So due to high means the energy released due to hydrolysis of Li is very high, hence the delta HF of the overall reaction becomes very much negative for Li. So due to very high hydration energy. Okay, hydration or hydrolysis energy, you can term it the way you want. So, and why is this the case? Because charge density on Li plus, the charge on Li charge density charge density is very high, this implies extent of hydration would be high. Charge density is nothing but charge of the cation divided by size of the cation. So Li would be having the least size among Li cation would be having the least size among all of these, hence charge density on Li cation would be the highest. So extent of hydration would also be highest. As extent of hydration is highest, hydration energy would be high. And as hydration energy would be high, delta H of hydration would be also more negative. Okay, so here we can write that charge density of cation is equals to positive charge in cation divided by size of cation. Okay, next, so in other words we can put that if a question of this sort comes that why is Li the strongest reductant among all the alkali metals when the CS metal has more ionization energy. So the simple reason would be that Li is the strongest reductant among all metals due to high hydration energy, which is due to the high charge density of Li cation when Li plus cation is hydrated in aqueous solution. Then high amount of hydration energy is released, which compensates is its low ionization energy, rather high ionization energy. Hence Li metal has a strong tendency to release valence electrons in aqueous solution than CS metal and act as a strong reductant. Okay, it's a fact that the ionization energy of Li is lower than cesium, but cesium has the ionization energy of Li is the highest than cesium. Cesium has the lowest ionization energy in all the alkali metals, because as we go down the group, ionization energy decreases. We have already seen this, but irrespective of that, even then the Li is a strong reductant than CS. Why? Because the hydration energy of Li is more than that of CS, because the charge density on Li plus cation is more, hence it easily releases one of the valence electrons and converts itself into Li plus. Hence it's a strong reductant even when the ionization energy of Li is highest in all the alkali metals. So with this we come to the end of this lecture. In the next lecture we'll be seeing more interesting facts. So till then, good luck and goodbye.